Hi, I'm Irvin, founder of DataSciU and creator of PixeLimit. Today we're excited to announce the availability of PixeLimit's free tier for academia. PixeLimit is an industrial-strength, no-code infrastructure to design, train, evaluate, and deploy ConvNets, all in the cloud with no local state. A ConvNet, or convolutional neural network, is a deep learning methodology for computer vision. In PixeLimit, a child can design a custom ConvNet in literally 10 seconds and moments later train it on the largest image sets in the world. Unlike PyTorch, TensorFlow, or the cloud frameworks, PixeLimit is the first machine vision framework to simultaneously offer industrial strength, a no-code development paradigm, no local state, but still full design control of your ConvNet, and finally, unprecedented introspection and visual debugging tools to help improve and debug your ConvNet. PixeLimit allows work with massive image datasets, such as ImageNet, with literally millions of training images that you can browse and process without ever having to download them. Training is performed on an array of mid-range NVIDIA CUDA-capable GPUs. Much of the functionality is offered free, and basic exercises don't even require a login. In addition to full control, you'll have transparency into the inner workings of your ConvNet with powerful visualization and single-stepping tools. Machine vision students and practitioners will find the design studio immediately intuitive. ConvNets are composed of a series of convolutional layers with small square operators that center around each input pixel to compute the output pixel for the next layer. These operators, 3x3, 5x5, etc., are composed of weights and biases, which are the trainable parameters of the ConvNet. The convolutional operators can be stacked in multiple channels to extract multiple features in parallel. There are also pooling layers to reduce the image size as higher level features are identified, and fully connected layers with a weight between each pair of input and output pixels. The final layer must be fully connected. Its output is one-dimensional, and its number of output values is the number of object classes that the ConvNet will recognize. Its outputs will sum to 1, expressing a probability distribution across the recognized object classes. After constructing your ConvNet, make sure the input size matches the size of your intended image set, and make sure the output size is the number of object classes to be recognized. For our example, we'll use the MNIST dataset of handwritten digits. MNIST is famous as the basis for the post office's handwriting recognition of zip codes. MNIST has 10 classes for the digits 0 through 9. So if we were doing the full MNIST exercise, we would configure an output size of 10. For this example, we'll just set an output size of 2 and teach our ConvNet to distinguish between two digits, say 3s and 8s. In the Train tab, select a number of object classes matching the number of ConvNet outputs. Use the slider to select the number of images to use for training. Here you'll want to avoid selecting the maximum so as to reserve some images for testing. Then click Train, and that's it. Weights will soon appear at right, indicating the best weights discovered so far. The combination of your ConvNet design and the learned weights is the trained object recognition solution. You can then proceed to the Test tab to test your ConvNet on other images. One thing you'll quickly learn is that to get any kind of above par result, you need to use a large training set. So while you may kick the tires with small training and test sets, you'll need to take the time with a substantial training set to get a satisfying result. For reference, the VGG19 ConvNet from Oxford, which can finally distinguish dogs from cats, took many days to train, although that would go much faster with PixeLimit's hyperscaled infrastructure. You'll also need a non-trivial ConvNet design. For a too simple network, it may not even be possible for it to distinguish the classes with any set of weights. Convolutional layers are feature extractors, while fully connected layers are linear separators. A common aspect of successful convnets is a series of final fully connected layers for repeated linear separation. For example, VGG19 has a final series of 3 fully connected layers. On the other hand, fully connected layers have many weights and so are hard to train. The structure of a convnet is a creative aspect of machine vision development and an area of intense research. For example, the VGG19 convnet has 19 layers. In PixeLimit, the equivalent convnet can be assembled in a couple minutes, and PixeLimit's no-code workflow won't let you make any mistakes matching up the layers' inputs and outputs. And you can train your convnet on the enormous ImageNet dataset just as the VGG19 convnet was. In the workflow, you'll see our mid-tier NVIDIA CUDA-capable GPUs offered in the cloud. PixeLimit performs super fast by stipulating that each mini batch of training images or test images must fit in GPU memory, with all layers and buffers that PixeLimit will allocate. Given a convnet design and input image size, PixeLimit indicates exactly how large a mini batch size will fit in GPU memory. This allows the GPUs to be utilized optimally. Despite this restriction, it will usually not be a limiting factor for your mini batch size. For example, the featured A10 GPUs with 24 gigabytes of memory can support mini batches with tens of thousands of images for most convnet configurations. You may be wondering what the underlying machine vision engine is. It is not one of the common frameworks like PyTorch. For PixeLimit, I have hand-coded a custom engine with GPU kernel functions in CUDA-C. The engine configures your convnet with all layer buffers and input images in GPU memory, with each layer having a reference on the GPU memory of the previous layer. During forward and backward propagation and gradient descent, image data never needs to be copied in and out. This is how PixeLimit gets its performance on a single GPU backend instance. Furthermore, PixeLimit deploys multiple such GPU backends to be orchestrated by a frontend in parallel. This allows multiple mini batches to be trained in parallel. And furthermore, for each mini batch, the gradient descent can be executed from multiple starting points in the weight space, again, all in parallel. You may have heard that GPUs run thousands of threads in parallel. That's not exactly true. A GPU implements a compute paradigm called SIMD, single instruction, multiple data. There's a single execution thread, but each instruction can operate on thousands or millions of values. For example, the same operation on 1,000,000 pixels. Or in our case, on 1,000 pixels in 1,000 training images. There is still some conditional logic, such as at the edge of an image or for divide by zero checks, and NVIDIA has invented some ingenious techniques to allow for conditional logic within a GPU kernel function. Machine vision research suffers from a burden of local state. The detritus of Python scripts, version frameworks, enormous data sets, models, and weight files. You never know whether some result or bug is an artifact of a given machine's state. When comparing designs, it's difficult to know whether you're doing a real apples-to-apples comparison. PixeLimit's academic offering eliminates all that for a class of students who all require equivalent setup. Furthermore, industry solution providers will appreciate not needing to maintain a code base and a loose set of model and weight files for each customer. We're doing early work serving the custom machine vision needs of reference partners, for example, identifying manufacturing defects. Those solutions are entirely saved and maintained within our database. Machine vision also suffers from a reproducibility problem. As a new and still unperfected field, it's full of exaggerated claims and selective demos. That's why we feel the industry needs a stateless platform where any result can be quickly duplicated and retried on fresh test data. The world is entering an era where individual ConvNets will have enormous business value. They will be in continuous training, searching for improved minima in the weight space, and retraining as new data arrives. It's sort of like a software code base that is continuously developed and periodically snapshotted and qualified for release. Thanks for listening about PixeLimit's free tier offering. With this and future offerings, you'll be able to test, share, fork, and compare ConvNet designs objectively and in collaboration, all with access to the largest available library of training images, or your own uploaded image sets. PixeLimit can host an inference service for your trained ConvNet and your custom application. It will serve your custom business need while also continuously training to improve its model. We'll also offer automated transfer learning where a pre-trained ConvNet is stripped of its final classes layer and a new layer substituted and quickly trained for a custom application. A one-click GAN offering is also in the works. A GAN is a generative adversarial network associated with a trained ConvNet and a single object class. One use of GANs is to generate synthetic training data for other machine learners, and Gartner predicts that by 2024, 60% of training data will be synthetic. On the inference side, we'll offer solutions like YOLO for identifying multiple objects in complex scenes, but applying your ConvNet. To learn more, see the training materials under the Learn tab or at the DataSciU Learning site.